Hello everyone. So in the last lectures, we discussed the beta decay, and prior to that we had discussed the alpha decay. And in all these discussions, our effort has been to explain the energetics of the decay as well as the decay probability. That is, somehow by a model we try to calculate the half-lives for the decay of these processes like alpha, beta. And so in the gamma decay also we'll try to discuss how to calculate the half-lives, and if you can predict the half-life for the gamma decay, and also what are the selection rules, so that in fact dictates the half-lives depending upon the different spins and parities involved in this one. The half-lives are changing, so we discussed that the selection rules for gamma decay. So gamma decay essentially is not from the ground state of a nucleus, but whenever we populate a nucleus in its excited state by alpha decay or beta decay, or it could be electron capture also. So if the nucleus is left in excited state, then the excited nuclear state emits gamma ray to come to the ground state. For example, the cobalt-60 having a half-life of 5.27 years undergoes beta minus decay to excited states of nickel-60, and these states are actually 4 plus, 2 plus and 0 plus. So this excited nuclear states of nickel-60 undergo gamma decay. So you have this is the very famous radioisotope cobalt-60 used in many applications. So this 4 plus state emits 1.173 MeV gamma ray to come to 2 plus state, and then 2 plus state emits a 1.32 MeV gamma ray to come to ground state. So these are the so gamma decay essentially takes place from the excited states of a nucleus, and these gamma rays they are photons, so they carry integral units of angular momentum, unlike the beta decay which carry half spin. Now the range of half-lives, what are the different values of half-lives? Range of the half-life for gamma decay spans. So gamma decay can take place in picoseconds also, or it can be in years also. So the ones which are emitting at more than picoseconds, nanosecond, microsecond, they will be called as the metastable states or isomeric states. So for example, 178 hafnium has got in fact two isomeric states, M1 and M2, and the half-lives are 31 years and let us say 4 seconds. So the half-life essentially depends upon the change in the angular momentum involved associated with the gamma decay. So half-lives of gamma decay can be from 5 picoseconds to years. The energy of the gamma ray, essentially the energy of the gamma ray is nothing but the spacing between the levels of the nuclei. So it could be from few keV to few MeV. So there are gamma rays of 50 keV also, there are gamma rays of 1 to 2 MeV also. And then from the probability for decay has been in fact calculated by Weisskopf using Weisskopf theory, that's called the single particle model, and according to which the half-life, if the energy is high, then half-life is short. So that means the higher energy gamma decay are more allowed. In a way you can say that allowedness depends upon energy also, and we will see more of it in subsequent part of this lecture. Now let us first discuss the selection rules for the gamma ray. So what happens actually when a gamma ray emission takes place? The gamma ray, like in atoms or molecule, when there is a excitation, absorption or emission of a photon, then we say there is a change in the dipole moment of the molecule. So essentially it is the change in the charge density associated with the transitions. So in the case of gamma rays, we will have two types of transitions called electric multipole EL, electric multipole, and magnetic multipole ML. So the electric multipole transitions are associated with the change in the charge density. So if there is a change in charge density, so like for example, if a nucleus vibrates, the charge density changes, and so we will have the associated electric transition. When we have a change in the current density, how do you produce a current? Suppose your electron is moving in a circular orbit, then it is generating a charge moving in a circular orbit, generating a magnetic field. So there are nucleons moving in the orbits of the nucleus, and there is a change in the current density in the nucleus. We say it is associated with the magnetic multipole transition. So the gamma transition is taking place. A single gamma ray can have either an electric character or the magnetic character. So we will discuss this more details as we go along. And so whatever the angular momentum that the gamma ray photon is carrying, we'll call it capital L, and it will carry the integral value of the angular momentum. So L could be 1, 2, 3, and so on, and that we call as the multipolarity of the gamma ray. So the multipolarity, depending upon the multipolarity, 1, 2, 3, 4, we can have. If L equal to 1, then 2 to the power 1, 2 to the power 2 raised to L is the multipolarity. So L equal to 1 we'll call as dipole gamma ray, L equal to 2 we'll call quadrupole, L equal to 3 octupole, L equal to 4 hexadecapole. So as we go to higher and higher L value, the transition becomes more and more hindered, because gamma ray, it is difficult for the gamma ray to carry large angular momentum. And in fact, when there is a excited nucleus, it has to emit gamma ray by changing a large angular momentum. And if it is possible, then it will find that the particle emissions, neutron, proton emissions, are more favored from the excited nuclei if the energies are more than the binding energy of nuclei. So the gamma ray essentially do not carry much angular momentum. So if it has to carry more angular momentum, that gamma ray decay is hindered. So now we will try to see how to classify this the gamma ray decay selection rules in terms of the change in the angular momentum delta I and the change in the parity delta pi. And depending upon the value of the delta I and delta pi, we can categorize a transition as EL or ML. We will see the selection rules very shortly. Okay. So the selection rules for the gamma decay essentially are similar to the selection rules for optical transitions in molecules or atoms. And taking the analogy from the molecular transitions like ultra UV visible transitions, then the matrix element for a decay and optical transitions can be written in terms of the wave function for the final state. It is the complex conjugate of that. The dipole moment operator for the electric transitions, E into R, E is the charge and the R is the distance, and psi is the wave function of the initial state of the molecule or nucleus. And then this is the volume, the g tau, dx, dy, dz over the volume of the system. So now this particular matrix element, we will say psi f star er psi I, it should be positive parity for a allowed transition. So the parity of the transition matrix, if it is positive, then we say the transition is allowed, and that will dictate the parity of the individual states psi I and psi m. For example, electric dipole operator ER. So how do you define the parity? Either -1 to the power L. Now, or if it is a function like psi, the function is changing sign when we go from x to -x, then we say this function has got odd parity. If it doesn't change the sign, we say even parity. So ER, essentially R is the distance, and so in x or R will be having negative parity, and so it's or the odd parity. So pi will be negative for electric dipole operator. Now, so one of the elements of this transition matrix is odd or negative parity. So if this function has to be allowed, then psi I and psi f have to be of opposite parity, so that suppose this is odd into odd, even into even. If it is even into odd, then odd into odd or even. So if one of them is odd, other has to be even for a electric dipole transition. That is how we decide what will be the parity of the two states. So if it is a E1 transition, L equal to 1, then -1 to the power L is negative. So parity for E1 transition is negative. So then psi I and psi F have to be of opposite parity. That means there has to be a change in the parity when we go from psi I to psi F. That means delta pi should be yes, means change in, there should be a change in parity. Yes, delta pi yes means there should be change in parity. And the magnetic dipole operator has opposite parity with respect to electric dipole transition, and therefore for M1 transition delta pi is known. That means if a gamma ray has to be of M1 type, then there should not be change in parity from II to IF. So that is how we decide the parity of the transitions. Just to give then also to elaborate it further, suppose you have an initial state of a nucleus, excited state, II is the spin of the excited state and pi I is the parity of that. And by emission of a transition of multipolarity L, it is decaying to a state, final state IF and parity pi. Then, so the angular momentum carried away by the gamma ray will be in the range of II minus IF to II plus IF. It can take that many values. Now, the lowest one is the most probable. So, when II equal to IF, then L cannot take 0 because 0 is not possible. Gamma ray has to be associated with the spin. So, L will take the value 1, 1, 2 to so to maximum value II plus IF because L equal to 0 is not possible. And also, it is important to note that if II equal to 0 and IF equal to 0, so 0 to 0 transition is forbidden for gamma decay. If II minus IF is 0, but then there could be II plus IF will be non-zero. So like for example here, so L can take anything more than 0. So 1, 2 to II plus IF. So that is how we'll decide the multipolarity of the gamma rays depending upon delta I and delta pi. So let us see here. So L can be decided based on this II minus IF to II plus F, and delta pi we will know from the functions. So if L equal to 1 dipole and delta pi is yes, then that transition will call EL, E1 transition. So electric dipole transition. And if L equal to 1 and delta pi is no, there is no change in parity, we will call it M1 transition. So that is how we classify the different transitions into EL and ML, where L can take value 1, 2, 3, 4 and so on. Similarly, when L equal to 2 and there is change in parity, then we say it is M2 transition. When L equal to 2, there is no change in parity, then we say E2 transition, because as we go to high, minus 1 to the power L, when minus 1 to the power 2, then it becomes positive, parity becomes positive. So accordingly, the rules will change, and you can just put the value for different transitions in terms of L and pi, and you can see whether it will be EL or ML. Now, in the case of EL and ML, the ML transitions are weaker than compared to EL transitions that we will discuss very soon. So if there is a ML and EL plus 1, for example, M1 and E2, then what will happen? This E2 starts competing with M1. And that then you will find that some of the gamma ray transitions have a mixture of M1 plus E2. But if there is a M2, there is a E2, then E2 and M3 is a weaker, so you will not have the admixture of E2 and M3. So similarly, E1 and M1, E1 is much stronger than M1, so you will not have a mixture of E1 plus M1. So only in case of M1 plus E2 or M3 plus E4 means the higher E can compete with the lower M. So you can have admixture of, and in fact there are experimental techniques to determine the admixture of the M and L. Now we will just see how we will just elaborate this, illustrate by an example of cobalt 60. In fact, cobalt 60 has got a very detailed decay scheme from the excited states of cobalt 60 2 plus state, which is having gamma ray emitting gamma ray 59 keV to 5 plus state. So let us see. We will see based on selection rules discussed previously. We will see the multipolarity of this transition, and this transition in this particular discussion. So for the first transition, let us say cobalt 60 M to cobalt 60 metastable state to cobalt 60 ground state. So it is 5 and 2. II is 2 and IF is 5. So it can take the value, L can take the value from 5 minus 2 to 5 plus 2. So you can have 3, 4, 5, 6, 7. And here the parity of both the states is positive. So there is no change in parity. Delta pi is no. Now you can see here when L equal to 3 and delta pi is no. You see here L equal to 3, delta pi is no. You will have M3 type of transitions. So predicted values of M, L are M3, E4, M4, M5, E6 and M7. And as I discussed, the higher multipolarities are having lower probability. So ideally it should be a M3 transition, but because E3 can compete with M3, so E4 can compete with M3, so we will have the observed value is M3 plus E4. There is a admixture of E4 with M3. So this is the type. This is how we can actually predict the multipolarity of a particular gamma ray transition. So for this, it is ML M3 plus E4. Now let us come to 1172 transition, keV transition. Here, this one. So that is the de-excitation of the excited states of nickel 60, the 4 plus state. So we have now 4 plus to 2 plus. So the gamma ray can take place 4 minus 2 to 4 plus 2. That means 2, 3, 4, 5, 6. So the gamma ray, so the 4 plus 2 transition, the L value can take 2, 3, 4, 5, 6. And the delta pi is no. So when the delta, there is no change in the parity, then you can see again here, delta pi is no and it is 2. So it is E2 transition. So we will have this as E2. And M3 cannot compete with this because M3 will be much weaker. Because it is the other way around. M2 can, with M2, E3 can compete. But with the E2, M3 cannot compete. So this will be E2 type. So the predicted is E2, M3, E4, M5. The predicted is E2 and the observed is also E2. Now let us come to this transition 2 plus to 0 plus. In 2 plus to 0 plus, we have 2 minus 0, 2 plus 0 is 2 only and no change in parity. So again, this also will be E2 times. So predicted value L equal to 2, delta pi no is E2, observed value is also E2. So that is how you can predict, and then experimentally there are experiments to measure the multipolarity of a gamma ray transition. So these are the selection rules for gamma decay. You can find out the multipolarity of a particular gamma ray. Now let's come second part, how to predict the decay constant for a gamma decay. So gamma decay constant, see the gamma ray probabilities, essentially we will just discuss in terms of the what is actually happening when there is a gamma decay. Say a nucleon is essentially getting transition from one state to other state. So for the gamma ray, the wavelength of the gamma ray can be given by this Hc by E. So we are actually defining here the reduced wavelength called lambda upon 2 pi, because this is called angular wavelength, because this is associated with the angular momentum. The gamma ray photon is carrying angular momentum, so we define in terms like angular momentum, we say h cross, 1 h cross h by 2 pi. Similarly, associated wavelength we say lambda cross. So the wavelength of a gamma ray we can calculate based on Hc by E. So you can see here, this is the H value, H 6.62 minus 27. This is the C value, H cross means H upon 2 pi, and you convert the MeV into joules, or joules into MeV. So it will become 1.974 minus 13 meters, where E is in MeV. So now let's compare this value with the radius of the nucleus. Typically for a nucleus of mass 100, you can calculate the radius in terms of R0 e raised to 1/3. That becomes 6.49 10 power minus 15 meters. So what essentially we want to highlight is that the wavelength of the gamma ray, for example, for a 1 MeV gamma ray, then the lambda cross is much larger than the radius of the nucleus, or the r by lambda cross is much less than 1. So the probability of emission or absorption of a gamma ray photon decreases with L as r by lambda cross to the power 2L. So why this has come? This has actually come from the Weisskopf's theory of statistical decay of the gamma rays. Essentially, it is that the wavelength, the wavelength of the nucleon inside the nucleus can be compared with the nuclear dimensions. So the radius of the nucleus is similar to the wavelength of the nucleon, and the wavelength of gamma ray is of the order of lambda. The lambda you can calculate. So r by lambda cross essentially dictates ratio of wavelength of the nucleon to the photon, and the probability of emission or absorption essentially depends upon this ratio of the two wavelengths. Secondly, the ML transitions are much weaker than EL transitions because the ML transitions are essentially associated with the velocity of the nucleon, and whereas the EL transitions are associated with the velocity of the light. So this is another factor. We can discuss this in terms of the moments, the magnetic moment and the electric moment. So we can derive, in fact, why does this ML to EL transition depends upon the V by C square. We can take the ratio of square of magnetic and electric moments. So the magnetic dipole moment of a nucleus can be written in terms of EH cross upon 2mc or EH upon 4 pi mc. This is the nuclear magneton. And electric dipole moment can be written as E into R. So the ratio becomes H cross upon mcr square, square of the ratio. Now for the nucleons, the reduced wavelength is equal to H cross by mv, and the nucleon wavelength is close to the R. So we can replace this R by H cross by mv in this formula. So the ratio of the magnetic dipole moment to electric dipole moment can be written as H cross by mc upon H cross by mv square. So it becomes V by C. So essentially, the magnetic transitions are associated with the change in the current. That means the nucleonic motion, which is associated with the velocity of nucleon. And the electric transitions are associated with the change in the charge density. So that is associated with the photonic velocity. So C. That is why the magnetic transitions are much weaker than the electric transitions. Now let us see how to calculate the decay constant in the Weisskopf's theory of single particle model. So Weisskopf's formula for the decay constant for electric transition is lambda E. This is the decay constant for the, not to be confused with the wavelength. Decay constant for the electric transitions is 2 pi V E square upon H cross C, the statistical factor, upon into R by lambda cross to the power 2L, where S is the statistical factor, the series involving the L values, and the lambda cross is the reduced wavelength of the gamma ray. So that is 197 by E, 1.974 minus 13 meter. If you write in Fermis, then 197 Fermis and in MeV. So now we can substitute this value R by this in lambda cross in terms of 197 by E. So the decay constant becomes this formula, E2 pi B E square upon H cross C SR E upon 197 to the power A. And if from this lambda value we can calculate the half-life or the lifetime. 1 by lambda is lifetime, because for the excited states normally instead of half-life we say lifetime. So for different electric transitions E1, E2, E3, E4, you can see the tau values are this, and for the magnetic transitions they are. So you can see the tau values are higher for magnetic transition because that means the lambda values are shorter. So the lambda value for magnetic transitions they are weaker than electric transitions. And one more thing is observed that these calculated values, they are in fact much higher than the observed values. The observed values for electric transitions are of the order of minus 13, minus 14 seconds, but you will see some of the observed calculated values are minus 9, minus 3. So this Weisskopf's single particle theory can give sort of order of estimates, but the large differences between calculated and experimental values essentially can be explained by other types of motions in the nucleus, like called the collective models. Collective motion, like the nucleus can vibrate, nucleus can rotate. So nucleus, in fact, this gave an idea. The fact that the experimental values of the half-lives of certain states are much lower than the single particle estimates by Weisskopf gave to the speculation that apart from the single particle model, that means the nucleons moving in their orbit, specified orbitals, the nucleus as a whole is undergoing collective motion, and that it has also got the collective states like vibrational states and rotational states, and then one can calculate the moment of inertia of the nucleus using the excited states of the gamma ray of the excited. So there is an evidence for the collective model of the nucleus also. Now, as I discussed that the higher L values are hindered, so there are alternative routes to excitation by gamma ray, and that is one of the internal conversion. This is an alternative de-excitation process in the gamma ray, or you can say it is a radiation-less transition, non-radiative transition. Instead of the gamma ray emission from excited state to ground state, that energy is used up in emitting an electron from the orbitals K shell, L shell, and M shell. So an electron from the atomic cells is ejected with energy E gamma minus the binding energy of that electron. So the energy of the electron, where does electron, suppose it is a beta decay. For example, mercury 203 emitting beta minus to thallium 203, and we have a continuous beta spectrum. Then these conversion electrons, the K electron, L electron, M electron, they will have sharp energy because their energies are well defined. Energy of gamma ray electron, K electron, gamma ray energy minus the binding energy of electrons is well defined. And so over a continuous spectrum, you will see these sharp peaks due to electrons, K electron, L electron, and M. So the energy of the K shell electron that is emitted will be lower because its binding energy is higher. So higher the binding energy of the shell, lower will be the energy of the electron. So different conversion electrons appear in the over the continuum spectrum. But in the case of electron capture, where there is no gamma ray beta emission, then the gamma ray conversion will be giving rise to sharp peaks in the electron spectrum. And you see the electrons, because of the K conversion, you will have the electrons at lower energy. So you can see here for K conversion 3.67 keV, L conversion 30.55 MeV, and M conversion 34.48 keV, and their percentages are also given in this. So conversion electron, whenever there is a large spin difference between the spin states of excited state and ground state, lower state, then you will find the gamma ray is converted. And it is a partly conversion, not that gamma ray is not emitted at all. Let's say you can say some percentage of gamma is emitted, some percentage of conversion electrons are emitted. So there is something called the conversion coefficient. It means what percentage of the gamma emission is converted, that will be called as the conversion coefficient. So the conversion coefficient is denoted by alpha. That is, it is like the branching decay. You recollect the branching decay of a nucleus into two modes, and that decay constant add up. So here the conversion coefficient is the ratio of decay constant for conversion electron and internal conversion and for the gamma ray decay. So, or you can also say number of conversion electrons upon number of gamma ray photons emitted. The ratio is called as the conversion coefficient. So you can measure the gamma ray and you can measure the conversion electron and find out the ratio to obtain the conversion coefficient. So the net decay constant lambda will be lambda E plus lambda gamma, because that is the like the decay constant add up. And so if you take lambda gamma outside, it becomes 1 plus alpha. That means lambda E by lambda gamma is alpha. And so depending upon whether you have the K conversion, L conversion, M conversion, we have K, alpha K, alpha L, alpha M. So alpha, the conversion coefficient, is sum of the individual conversion coefficients. So higher the multiple order, the higher the alpha K. So as for lower multipole value, gamma ray decay is more probable. For higher multipole value, conversion is more. And this is true for alpha L, alpha M also. Similarly, with regard to Z, if the Z of the nucleus is high, then conversion coefficient is high. If the energy of the gamma ray is high, conversion coefficient is low. So internal conversion is more favored with gamma ray of low energy with and the higher atomic number nuclei in higher multiplicity. So there are a lot of experiments people do to determine the conversion coefficient K by L ratio also, and that tells you about the multipolarity of the gamma ray. Lastly, I have already discussed the nuclear isomers, so don't have to discuss much. These excited states of nuclei having lifetime more than picosecond, that living beyond the single particle estimates will be as wherever there is a gamma ray decay is hindered. And you can see typical example, barium 137M, 2.5 minutes. You can see large spin difference, technetium 99M, half minus to 9 by 2 plus, xenon 125M, 59 by 2 minus 2 half plus. They are having gamma decay as well as conversion also. But barium, bismuth 210M, see for 6 years, and this gamma decay is totally hindered. It is emitting alpha decay because there is large difference, 9 minus to 1 minus. So nuclear isomers are there, particularly near the mid shell nuclei or near the closed shell closures. The nuclear isomers are very common, and essentially their existence is due to the large spin difference between the two excited states and the ground state. So we will discuss this more in the when we how to detect these nuclear isomers. One can develop methods for determining their lifetimes. There are methods to determine lifetimes. So we will discuss more now on detection of these different types of radiation in subsequent lectures. As of now, I'll close here. Thank you very much.